very difficult to make this on Mars because there's no oil. So really quite difficult to make the propellant on Mars. And then propellant transfer is pretty good, but not great. Hydrogen, although it has a high specific impulse, is very expensive, incredibly difficult to keep from boiling off because liquid hydrogen is very close to absolute zero as a liquid. So the insulation required is tremendous, and the cost of the energy cost on Mars of producing and storing hydrogen is very high. So when we looked at the overall system optimization, it was clear to us that methane actually was the clear winner. So it would require maybe anywhere from 50 to 60% of the energy on Mars to refill propellant using the propellant depot, and just the technical challenges are a lot easier. So we think methane's actually better on just really almost across the board. And we started off initially thinking that hydrogen would make sense, but ultimately came to the conclusion that the best way to optimize the cost per unit mass to Mars and back is to use an all-methane system, or technically deep cryomethalogs. So those are the four elements that need to be achieved. Whatever architecture, whatever system is designed, whether by SpaceX or anyone, we think these are the four features that need to be addressed in order for the system to really achieve a low cost per ton to the surface of Mars. And this is a simulation of the overall system. So what you saw there is really quite close to what we will actually build. It will look almost exactly what you saw, like what you saw. So this is not an artist's impression. These the simulation was actually made from the SpaceX engineering CAD models. So this is not, it's not just, well, this is what it might look like. This is what we plan to try to make it look like. So in the video, you got a sense for what the system architecture looks like. The rocket booster and the spaceship take off, loads the spaceship into orbit. The rocket booster then comes back. It comes back quite quickly, within about 20 minutes. And so it can actually launch the tanker version of the spacecraft, which is essentially the same as the spaceship, but filling up the unpressurized and pressurized cargo areas with propellant tanks. So they look almost identical. So this also helps lower the development cost, which obviously will not be small. And then the propellant tanker goes up, and it'll go up multiple times, so anywhere from 3 to 5 times to fill the tanks of the spaceship in orbit. And then once the spaceship the tanks are full, the cargo has been transferred, and we reach the Mars rendezvous timing, which, as mentioned, is roughly every 26 months. That's when the ship would depart. Now, over time, there would be many spaceships. You would ultimately have, I think, upwards of 1,000 or more spaceships waiting in orbit. And so the Mars colonial fleet would depart en masse. They're kind of like Battlestar Galactica. You've seen that thing. That's a good show. So a bit like that. But it actually makes sense to load the spaceships into orbit because you've got 2 years to do so, and then make frequent use of the booster and the tanker to get really heavy reuse out of those. And then with the spaceship, you get less reuse because you have to say, well, how long is it going to last? Well, maybe 30 years. So that might be 12 to maybe 15 flights of the spaceship at most. So you really want to maximize the cargo of the spaceship and reuse the booster and the tanker a lot. So anyways, the ship goes to Mars, gets propellant replenished, and then returns to Earth. So I'll go into some of the details of the vehicle design and performance. And I'm going to gloss over, I'll only talk a little bit about the technical details in the actual presentation, and then I'll leave the detailed technical questions to the Q&A that follows. This is to give you a sense of size. It's quite big. And the funny thing is, I think in the long term, the ships will be even bigger than this. I think that this will be relatively small compared to the Mars interplanetary ships of the future. But it kind of needs to be about this size because if in order to fit 100 people or thereabouts in the pressurized section, plus carry the luggage and all of the unpressurized cargo to build propellant plants and build everything from iron foundries to pizza joints to you name it. We need to carry a lot of cargo. So it really needs to be roughly on this order of magnitude, because if we say like say a minimum threshold for self-sustaining city on Mars or civilization would be 1 million people. Well, and you can only go every 2 years. If you have 100 people per ship, that's 10,000 trips. So I think at least 100 people per trip is the right order of magnitude, and I think we actually may end up expanding the crew section and ultimately taking more like 200 or more people per flight in order to reduce the cost per person. So, but it's 10,000 flights is a lot of flights. So you really want, ultimately, I think, on the order of 1,000 ships. It'll take a while to build up to 1,000 ships. And so I think if you say, when would we reach that million person threshold, from the point at which the first ship goes to Mars, it's probably somewhere between 20 to 50 total Mars rendezvous. So it's probably somewhere between maybe 40 to 100 years to achieve a fully self-sustaining civilization on Mars. So that's the sort of a cross-section of the ship. And in some ways it's not that complicated, really. It's made primarily of an advanced carbon fiber. The carbon fiber part is tricky when dealing with deep cryogens and trying to achieve both liquid and gas impermeability and not have gaps occur due to cracking or pressurization that would make the carbon fiber leaky. So this is a fairly significant technical challenge to make deeply cryogenic tanks out of carbon fiber. And it's only recently that we think that the carbon fiber technology has gotten to the point where we can actually do this without having to create a liner on the some sort of metal liner or other liner on the inside of the tanks, which would add mass and complexity. So it's particularly tricky for the hot gaseous oxygen pressurization. So this is designed to be autogenously pressurized, which means that the fuel and the oxygen, we gasify them through heat exchanges in the engine and use that to pressurize the tanks. So we'll gasify the methane and use that to pressurize the fuel tank, gasify the oxygen, use that to pressurize the oxygen tank. And this is a much simpler system than what we have with Falcon 9, where we use helium for pressurization and we use nitrogen for gas thrusters. In this case, we would autogenously pressurize and then use gaseous methane and oxygen for the control thrusters. So really, you only need 2 ingredients for this, as opposed to 4 in the case of Falcon 9, and actually 5 if you consider the ignition liquid. So we use a sort of complicated liquid to ignite the engines that isn't very reusable. In this case, we would use spark ignition. So this gives you a sense of vehicles by performance, sort of current and historic. I don't know if you can actually read that, but in expandable mode, the vehicle approach that we're proposing would do about 550 tons and about 300 tons in reusable mode. That compares to Saturn's V max capability of 135 tons. But I think this really gives a better sense for things. The white bars show the performance of the vehicle, like in other words, the payload to orbit of the vehicle. So you can see essentially what it represents is what's the size efficiency of the vehicle.